introduce Ramin Hasani. So Ramin finished his bachelor in Iran, and he got to Tecnico di Milano as on an award of exceptional student. I was fortunate to be able to recruit him afterwards because he was working on neural networks. Actually, he was implementing them in hardware in Milano. And so I was able to recruit him in my group, where he did an outstanding job. And now he's a postdoc at MIT, in the group of Daniel Arras, and I'm sure he's continuing his great activity over there. So Ramin, the floor is yours.
Thank you so much, Radu. All right, hi everyone. I'm going to describe today a kind of technology we have been working on with Radu and Daniela for a couple of years now. And this is a class of continuous time neural networks called liquid time constant networks. So let's get started by defining what is a time continuous neural network. So a time continuous neural network determined by a flow of hidden states, X, and its flow is identified by a neural network F, number of which is given by a number of layers N, and then the width K, and a type of activation function. And then it's a function of its hidden states. That means it can have feedbacks. It's a function of its input, and it has model parameters theta. So with this kind of terminology, it can give rise to dynamical systems, functions that we previously wouldn't be able to produce with normal neural networks. So it was recently shown that they can be equivalent, they can be the continuous depth equivalent of a residual network that basically in a residual network or typical neural network, we have a finite transformation of computation graph, which is equidistant. Basically, at each layer, we are computing basically an output for a neural network. But then when you use a time continuous neural network, you can have adaptive computation, and you can transform the space into a vector field where you can actually have a very efficient computation at arbitrary point based on the type of numerical ODE solver that you use. So to elaborate a little bit more about the features of time continuous networks, let's see how a standard recurrent neural network discretized, like a discretized version of a continuous flow, which was developed in the 90s. And then, so this is actually the transformation that you can have computing your next value given a neural network that has recurrent connections, inputs, it's a function of time or inputs, input sequences, and it's parameterized by parameter theta. So this is actually the transformation of a recurrent neural network. And then a neural ODE or a time continuous network, the representation becomes a differential equation. And then a more stable version of this is called a CTRNN. And a CTRNN is basically just the same differential equation with a damping factor tau that give rise to a more stable neural network. Now, if I just want to show you like how different they are in modeling time series, I can show you like the top part, which is a discretized recurrent neural network, the power of prediction and extrapolation of a typical standard recurrent neural network is actually looks like this. And this transformation is much more smooth when we are using a continuous time recurrent neural network. And that's one of the benefits that we can get out of these systems. So how do we implement these time continuous neural networks? Given a neural network by this differential equation, then we can take advantage of numerical ODE solvers. So we can write their equation, we can approximate them, their next value by for example, an explicit Euler kind of discretization. And then we can get the next value based on this differential equation given here by defining this delta t. Now, this is called a forward pass. A forward pass computes for you the next value given the current state and the current inputs to the system. So the forward pass can be identified by any type of numerical integrator or numerical ODE solver. So this numerical choice of the ODE solvers actually identifies the forward pass complexity. Now, how do we train them? So you can use a method that is called adjoint sensitivity method. Again, every time we want to train a neural network, what we want to do, we want to define a loss function that let's define our neural ODE by this function. And the flow of neural ODE in time is given by this figure over here. At every given point in time, we are being able to compute a loss. And then this loss can be computed by a kind of a call to an ODE solver that receives your first input and that does have the neural network F. And then it wants to arrive at a final point. And then basically you want to sum up all those losses that you compute based on the loss function, given loss function to compute the loss value. So adjoint sensitivity method wants to take at every single point, run an auxiliary differential equation, this adjoint state, that is corresponding to the derivative of the loss in respect to the state of the neural network. That means at every given point, if we run this differential equation, this would be a backward run to the same ODE solver to basically compute the previous value of the loss so that you can compute the gradients in respect to the loss with one step. And then at the current step, you can do one more gradient propagation, and you would not require to propagate back throughout the whole sequence. This will give you a complexity of 1. Basically, it's a constant complexity when you use adjoint sensitivity method. Then there is another method to compute this. It's called backpropagation through time. It's a classical method where we have a forward pass, and then given a forward pass, what you want to compute, you want to just go through the ODE solver, like how we are discretizing this ODE, and then computing the loss gradients one by one, and then using the chain rule to compute your gradients. And then you can update your old parameters by new parameters. So I showed you how to do forward pass and how to do backward pass. Which type of these trainings to use depending on the situations, because the backpropagation through time itself comes with a really, really significant computation, but it has its own advantages. So the advantage of using backpropagation through time comes with an error that is caused by the adjoint sensitivity method. Imagine if I show you a continuous vector field like that, and if I give you an initial value for a system, then you can run this system. Then this is actually the actual forward run of the system. Now for the adjoint time where we want to make the reverse transformation, the ideal transformation was to actually go back directly over this trajectory, but actually the adjoint ODE solver can give rise to numerical errors for the latent errors. So, and in general, just want you to show that the memory, it is true that we gain memory complexity, but we actually lose backward accuracy. So, I mean, in cases where compute doesn't matter, then you can actually stay with vanilla backpropagation through time, which is a better model. Now, neural ODEs and defining neural networks in terms of differential equations have a lot of advantages. And in principle, in theory, they should be extremely good for kind of tasks that deal with sequential data and continuous time spaces, such as robot control, a variety of robot control tasks that I'm showing here. So can a neural, but so far we haven't seen in the literature that a neural ODE in the form of a recurrent neural network can actually be as expressive as advanced RNNs in real-world applications. So there has to be a more expressive way to show neural ODEs, because with this current form, they cannot beat the state-of-the-art classical recurrent neural networks. So with this motivation, we decided to look at the problem differently. So we gave rise to a category of neural networks that their hidden state are actually computed by a very simple linear ODE. And this linear ODE has a damping factor or a time constant tau, which is a constant value, and receives a specialized input S. This specialized input S now is identified by a neural network multiplied by the difference of a parameter, of a biasing parameter, minus the state of the neural network. So with this definition, if I add this S inside the equation 1, what I can get a more complex representation of an ODE that has special characteristics. For example, as we see here, the coefficient of x of t in this equation was only tau, a constant value. So, and this coefficient actually defines the characteristics of this differential equation, given no input, autonomous kind of behavior of the system. Now, the coefficient of x is defined by the neural network itself. So that means at every given time point in time, we would have a different dynamical system that is adaptable to the environment. So defining basically the state of the neural network would be solution of this initial value problem, and then which has a variable time constant. The neural network F also appears in the state, in defining the state of the differential equation, and also inside the time constant element or the coefficient of X element, which is different. And we recently showed that this system actually comes with a lot of attractive behavior. For example, if I call this coefficient a time constant of the system, and also defining the whole state of the neural network X of t, we showed that even if the inputs to this system goes to infinity, the time constant of the system, this time constant of the system, for every nodes inside the neural network is actually stable and is bounded between two, like lower bound and upper bound. We also showed that the state itself for every neuron or every node inside these liquid time constant networks or LTCs, they're also bounded. So that's also another nice property of these networks. Another property of this network is that, like, I arbitrarily chose a kind of differential equation for myself, and then is it a universal approximator or not? Can we approximate any kind of dynamics by an arbitrary precision with these networks? Then we also follow the kind of principles of universal approximation for neural networks to actually show that this system also has universal approximation capabilities. But then how deep and how these neural networks are basically more expressive. Like, universal approximation applies to all types of neural networks. How can we distinct between like shallow networks and deep networks? So for actually digging a little bit deeper into the foundation of how expressive are these liquid time constant networks, we used one of the nice definitions that the deep learning community actually came up with. It's called the trajectory lengths measure of expressivity. Imagine you have a trajectory, a 2D trajectory circle, and you want to input this trajectory inside a neural network, a normal neural network. And then what you have a neural network with n layers and with k, and its weights are actually sampled from this n. Then the observation was that if you project the trajectory, input trajectory to this system, layer by layer in this neural network, we see that the complexity of these trajectories increases by the number of layers. Not only the complexity of this increases, but also if we compute the lengths or arc lengths of this trajectory, this arc length has a lower bound that is exponential in the number of layers. That means the length here is your neural network. The more the deeper is your neural network, the more expressive you might get based on this trajectory lengths. So that's a measure of expressivity that sets the boundary between shallow networks and deep networks. So we try to formulate the same thing and apply this to a couple of continuous time recurrent neural network algorithms, neural ODE architectures, and LTCs. And then we project back the activity into 2D for this basically continuous time neural networks. And we observed that continually, we saw that the trajectory lengths in 2D for the LTC models are basically longer and more complex. For example, here, we show that if you're just changing the weighting initialization of the neural network, you can create extremely complex patterns by LTC networks, while the complexity and the lengths of the trajectory of the neural ODE and CTRNNs are basically stays very, very uniformly. And then we also try to extend this to actually see that by changing the many variables inside these architectures, can we actually keep our interpretation of this system? So can we actually prove that these systems are more expressive in terms of trajectory lengths? And that's actually the case. So the yellow line here in all curves, where we are showing into different ODE solvers, different network width, then we have initialization, weighting initialization scale, and also network layers. Then we also approved some lower bounds we found some lower bounds for the trajectory lengths or the expressivity of neural ODEs, CTRNNs, and LTC representations. And then based on that, we actually validated that our theory actually works. And also our experimental results are kind of validated. So if these systems are more expressive in theory, then how would they compare against the state of the art in real world applications? For example, if you look at the movement of cheetah, we can see that if we want to model that behavior, then LTCs outperform LSTM policies, continuous time GRU units, and neural ODEs as well. If we compare them in a real world application of person recognition, person pattern, this is a data set where it's like a time series of activity of a human body, and you want to classify sequence of behavior into certain pattern. We see that LTCs are also kind of performant. We also took a couple of real world applications, and then we saw that in most cases, LTCs are outperforming other models. And now what I want to show in summary so far to you is that we introduced this model. We showed that it's universal approximator. We showed that it has a stable dynamics, and also they show better degrees of accuracy, expressivity, and they can vary their behavior even post-training because of the liquidity. And so these systems are also good for irregularly sampled data. One of the examples that I showed you, like the tables, we benchmark against this irregularly sampled data, and they can actually model continuous time processes pretty effectively. But now, can we scale the applications of LTC into even larger networks? Because the examples I showed you, these are all small examples, and something with larger impact, and maybe even exploit what is actually possible to do with this type of modeling system. For example, how can we apply this system to end-to-end control of cars, like autonomous driving, where we collect a bunch of human data and then we want to perform the driving activity. So in the current autonomous vehicles that are camera-based, for example, Tesla Autopilot, we have some sort of, like the inputs are RGB images. They actually go through a kind of cascade of layers of convolutional networks, followed by fully connected layers that actually shape up the whole thing as like 20 to 100 million parameters. Or let's say, like, you can even scale it down from 5 million to, let's say, 100 million parameters. This system can actually drive a car end to end. Then what we actually try to ask is that what happens if we can actually replace the fully connected layers where we have an overload of parameters, training parameters, with recurrent neural networks? And what happens if we use LTC-based networks and then compare the performance of 4 different architectures where we have LSTMs as a control unit right after convolutional layers? We have CTRNNs or neural ODEs, basically, right after the convolutional layers, the convolutional neural network, and an architecture we call this, just based on a network of LTC systems, is a 4-layer specific architecture, which we call neural circuit policies, which is built by the LTC model. And we want to see what can be gained if we actually formulate this. It turns out that to do the autonomous driving in real world, we would need only 19 neurons of NCP neurons with a much smaller convolutional neural network and much smaller number of trainable parameters. That's one of the advantages of having an expressive model inside a larger scale problem. Another aspects of these networks is, I would like to talk over it like with this video. So this is now a normal convolutional neural network with fully connected layers. And these fully connected layers are showing here the activity of the fully connected layers while the driving is happening, because this is the input to the neural network. The neural network has to decide about how to actually go about the driving. We see that a convolutional neural network, this is actually what is out there right now, similar to this architecture, is over the Tesla Autopilot. So what we have here on the bottom here, what I'm showing is the attention map of the convolutional layers while the driving is happening in this tree. So we see that the convolutional neural network is attending to this roads sideways to make a driving decision. Mostly that's the case when the driving happens. If I add a little bit of noise over this, what we see is that the attention map or the decision of the networks are not reliable anymore. And that's one of the fundamental problems. It is true that a convolutional network can actually solve this problem, but also their decisions are not going to be reliable anymore. Instead of that, if we actually use an NCP network, which only has 19 neurons, basically what you get is an attention on the road's horizon. So basically, it's kind of capturing the main causality of the data. And also, even if I add noise on my data, look at the attention map. It is definitely affected by the noise, but what we see is that its concentration is mostly preserved. So its decisions are more robust compared to other networks. Here, what I'm showing you is a time sequence of inputs to a neural network with LSTM networks. This is the attention map of an LSTM network, attention map of neural ODEs, convolutional networks, and NCPs. We see that there is actually a consistently focus on the horizon while we are using an NCP network. And that's one of the very nice features of these networks that we actually explored and found empirically. Another thing that we found is that the number of crashes, like imagine on the x-axis, I'm increasing the amount of noise, And the y-axis, I'm measuring the number of crashes that would happen in real world. Then we see that NCPs, the ones that is on the lower side, is actually much more resilient to perturbations. Another recent work that we were actually looking at was in what is the underlying principle? Like, can we actually mathematically talk about, is there really, like, this liquid time constant network, LTC networks, are they really causal models? That's actually another work that is under revision right now, where we actually show theoretically that a system composed of, let's say, a dynamical causal model with two neurons. Let's say we have two neurons and they're connected through these synapses together. Dynamical causal models would allow intervention from outside world onto the synaptic parameters of two neurons that are interacting with each other. They have an internal coupling, and they have basically a fixed parameter that controls or tunes the inputs directly to this xi, or the neuron number 2. And then if we have an analogy to the liquid time constant networks, we see that we would have the same type of constants, but here we have a kind of nonlinearity. We have a nonlinear control that is controlled by a neural network. So a neural network actually controls how the interaction between two neurons are basically formed. And this is actually where the liquidity modulator, or a nonlinear liquidity modulator, is actually coming up. And this is what we found in the paper. And then what we showed it on a task of drone navigation. So what you're seeing is that there is a drone that is learned only by visual inputs to actually move towards a target. So we see that on the right-hand side, what we see is that as soon as the drone realizes that there is a target, all the attention of the NCP network actually comes on the target. And that's actually something that came without even coding this and without any inductive bias inside the system. We also tested it on multi-agent systems. So what I'm showing here is a view from a first drone or a follower drone, and the drone inside the environment is actually a leader drone. And then the follower drone actually learned how to attend to this second drone while performing a task of leader following. And now in the leader following task, if we look into the attention of the network, like this is the view from the first drone to the second drone, which is here, we see that the attention of the network is actually on the first drone. And this is actually one of the really cool observations, that we could connect LTC networks as causal models. So they are actually causal models as well. I would like to thank you for your attention with this, and would like to invite you. I also like to thank my collaborators, Radu, Daniela, Alexander, and Matthias. And so that we have open sourced all our kind of technologies. You can actually get access in both TensorFlow and PyTorch if you want to get hands-on. And with that, thank you for your attention.
Thank you, Ramin. This was super exciting. I'd like to open the floor to questions. The chat will work, or a microphone will work.
So I have a question, Mr. Radu. So why do you think these networks are more expressive than let's say, classical neural ODEs?
Yeah, so one of the things is that we use this measure, like we use the expressivity measure, which was the, like the trajectory lengths. The trajectory lengths is actually one of the nice measures in deep learning community, where it actually unifies. For example, one of the measures of expressivity in deep neural networks is number of linear regions that, as a result of like adding neural networks, you would have a space. Let's say you have a 2D space, like a really abstract 2D space. So the more ReLU networks you add, the more number of regions you create inside the space. So basically it measures the number of complexity. But then trajectory length is a better measure for expressivity, and it was shown in a paper in 2017 that is actually a good way to measure expressivity of a network. So we theoretically figured out that these networks are more expressive.
And by how much? I mean, is it like linearly?
Well, I mean, I showed
exponentially better.
Yes, in some cases it's exponentially better depending on what you're. So this is actually the trend. So let's say if I increase the size of a neural network, then the yellow line here is basically first of all, an order of magnitude, the length of the trajectory is higher, and at the same time the trends are kind of similar. Okay, like the trend, how the complexity can increase. Okay, and then there is also an exponential increase in the how you're initializing your weight values. Imagine your weight values of your neural network are of these orders, and then you have an exponential increase in all, but in overall LTCs are better than the others.
Thanks.
Thank you. I would love to ask a few questions, but in the interest of time, thank you, Ramin, for the great talk. And we'll move to the next speaker. Mayur Naik is here. If Mayur, do you